Okay, hi everyone, and welcome to our talk. I won't repeat the name again. As for the speakers, I believe this is the only talk that has 3 speakers, so make of that what you will. I won't go through each of our names since we've already been presented. A quick look at the agenda for today's meeting. And without further ado, let's get into it. First of all, who's Alchemy? Never heard of them. So who we are and what we do. Alchemy is the leading Web3 developer platform. We are currently powering over 70% of the top blockchain apps. So if you've ever used the services of OpenSea, Circle, or WorkCoin, you've actually been using our infrastructure under the hood. It was founded in 2017 by 2 Stanford alumni. It is currently valued at $10.2 billion, while also being backed by Pantera, A16Z, and Coinbase. As for what do we actually do, we run RPC nodes across over 200 networks, so for chains like Ethereum, Polygon, Solana, Base, and many more. These RPC nodes are being backed by our Cortex engine, which handles over 10 billion requests a day while providing 4 nines reliability and also WebSocket connections. We also provide SDKs in all major languages, enhanced APIs, and account abstraction tooling. And for the Romanian connection, in 2024, Alchemy acquired Bureau Labs, which was based right here in Bucharest. And since then, Bucharest has become one of our key engineering hubs working on mission-critical infrastructure. Now, before we get into how we actually run blockchain nodes at scale, let's take a step back and go through a bit of blockchain fundamentals, like what is a blockchain node, because I have no idea. At its core, a blockchain node is basically just an application that has 2 layers, consensus and execution, which are usually packaged as 1 or 2 binaries, executables that you run on a machine. First, you have the consensus layer, which is the part that talks to every other node in the network in order to agree on the ordering and the validity of blocks. So here comes protocol like proof of stake, if you've ever heard of it. Basically, its whole job is making sure that every participant in the network agrees about what happened and in what order. And on the other hand, you have the execution layer, which actually does the work. So processing transactions, running smart contract logic, and maintaining the current state of the blockchain. So things like account balances, token holdings, and contract storage, all of that lives within this layer. Now, you might ask yourself, how do these nodes communicate with each other, since there is no central server coordinating everything? Information gets gossiped through a peer-to-peer network, so whenever a new transaction or block comes in, the nodes pass along to their peers, who pass along to their peers, and so on and so forth until the entire network is in sync. On top of that, these nodes maintain their own local copy of the blockchain state, and depending on how you can configure it, you can retain the full history going back to the Genesis block. So in cases like Ethereum, that could be terabytes of data, or maybe just a small snapshot, which is more lightweight, but still enough in order to validate new blocks. So we know what a blockchain node is. Now let's talk a bit about the types of blockchains there are. First of all, we have the layer 1s. The layer 1 is the base blockchain that provides its own security, its own consensus mechanism, and final settlement. So these are the blockchains that stand on their own, so Bitcoin, Ethereum, Solana. When a transaction is finalized on L1, that's kind of it, and that represents the source of truth. However, there is a small problem with layer 1s because they can only process so many transactions per second. And that's where layer 2s come in. An L2 is a scaling layer built on top of an L1 that processes transactions off-chain, meaning outside of the main chain, while inheriting the security guarantees of the L1 underneath. So you get faster and cheaper transactions without sacrificing the trust guarantees. Now, the most common type of L2 today is a rollup, and a rollup, as its name suggests, rolls up hundreds or even thousands of transactions into a single batch, and then posts that data along with a proof or summary back to the L1. So instead of the L1 processing every individual transaction, it just verifies the one batch. And since you already post the data to the L1, you also inherit the security guarantees. Now, there is an important distinction here to make because all rollups are L2s, but not all L2s are rollups, because there are other approaches like state channels or Validiums, but rollups have been the dominant solution by far, and they have become a significant part of what we're dealing day-to-day at Alchemy. Okay, so we went through the blockchain fundamentals. Now let's go and see why we're actually here, our journey to cloud native. When we first started, everything ran on AWS in Kubernetes, and that kind of makes sense, right? Because it's flexible, easy to spin things up, and you can also scale on demand. However, there's a bit of a problem, and you might have already guessed it, that's cost. Because when you run hundreds of blockchain nodes, each one needing significant compute and storage, those cloud bills actually add up really fast. So we're talking about workloads that need to run 24/7 and need to keep up with the chain in real time. So the pay-as-you-go pricing did not really fit our current needs. So in order to solve this, we transitioned to bare metal, where you get fixed and dedicated fixed costs each month for dedicated hardware, and that is much easier for us instead of going through your AWS bill at the month and see that you have a lot to pay because one chain had a busy week. Also, bare metal did not come that easy because it also had its own set of challenges, especially around scaling, because the databases behind these nodes can grow to be tens of terabytes of data. And when you're moving that much data around, whether it's, I don't know, syncing a new node, rebalancing storage, or maybe recovering from a failure, it is not trivial. So in order to accommodate this, we leveraged private networking in order to get some faster transfer speeds and just cut down on those times. And also, the other elephant in the room is the unpredictable load, since blockchain traffic is inherently unpredictable. So you can have quiet periods and then sudden spikes in traffic when there is a new popular NFT or a market event going on. So in the bare metal world, the reality is you just end up over provisioning. You buy more capacity than you need, just so you can handle those peak times. Oh, sorry. Wrong button. Okay, so we went from Kubernetes to bare metal, and now we're actually circling back and going back to Kubernetes, but this time on top of bare metal, and let me explain why. Because with the rise of rollups, things have actually changed. Clients started wanting their own chain, and since there are only a couple of frameworks to build rollups on, like OP-Stack or Arbitrum Orbit, spinning up a new node for a client was merely a config change. So same executable, but different parameters. We suddenly went from managing a few dozen large deployments to managing hundreds of smaller ones. So we need a way to optimize those workloads more efficiently, and obviously that's where Kubernetes comes into play. So the thing is about these rollup nodes is that they were really tiny. So a lot of them were using as much as 10% of the resources of the machines they were sitting on. So that's a lot of wasted capacity, because when you're in the bare metal world, you're paying full price for a server for it to only do a fraction of its job. So that's a lot of waste. And obviously that's another point for Kubernetes, because Kubernetes gives us the ability to bin pack multiple nodes onto the same machine, scale them independently, and manage hundreds of deployments without it becoming an operational nightmare. So what we did, we combined the two. We're running Kubernetes on bare metal, and that is what we actually call the RPC platform, because we get the scheduling flexibility of Kubernetes, the resource optimization, while still keeping the predictable economics of bare metal. So best of both worlds, as one might say. And now I'll let my colleague Mihai explain you what exactly RPC platform is.
Thanks, Mihai. I think you closed. Okay, sorry. So, hi everyone, thanks for being here. My name is Mihai Mihalcea, and today I want to present our cloud native journey, and also I want to talk about our challenges that we encounter in our daily operation. So I will start with the RPC platform, the system that we build to run blockchain nodes at scale. Before starting, I want to mention something very important. When I'm saying nodes, I'm not talking about Kubernetes nodes, I'm talking about blockchain nodes. For the servers that run Kubernetes on top of it, I will use the word host. So the blockchain nodes are resource-hungry piece of software. So running them can take a lot of disk. I mean, for the data, you can consume terabytes of disk, and also you need to wait a lot of time for the syncing process, and these nodes needs to stay available and responsible 24/7. Now, imagine running over 200 networks like this in a reliable manner across multiple regions, and serving millions of requests from multiple users or application that depends on low latency. From a tooling and operational perspective, we are using cloud-native technologies. We use Ansible for infrastructure provisioning. We are using Helm for template packaging, Argo CD for GitOps-based deployment and drift control, Server Manager for automate the TLS certificate, Prometheus for monitoring and alerting, and many more. But somehow we run into a key limitation because the Kubernetes resources don't fully address our requirement, our operational requirement. So we implemented and designed an operator tailored specifically to fulfill our scheduling and scaling needs. I will continue presenting the architecture and how request flow works end-to-end. So we are running Kubernetes clusters across multiple regions. Right now, we are in US region and Europe Central, but we are planning to extend in other regions. Each Kubernetes host is a high-performance worker node that needs to be able to handle the event of running one or more blockchain nodes and its storage. This is somehow the problems that we are facing in our daily operation. So now you can see a cluster footprint in the right upper corner. You have something like 800 CPU, 15 terabytes of RAM, and 1.5 petabytes of disk. But let's see what happens when a client reaches our cluster. So you can see from the right to left, a client that can be a user, an application or an internal services, make an RPC request. Think of it as asking the blockchain node a question like, hey, give me your latest block, or hey, give me your chain ID. This request first hit our smart proxy layer, Cortex. And this layer, it's a routing layer that know about which networks are available in our cluster, which nodes are healthy and fully synced, and also which region can respond with the lowest latency. Based on this context, Cortex will route the request in the optimal region on the optimal node. So, for example, if we have a ZK Sync node in the Europe region, and this is the best option for a certain request, the Cortex will route the request there. But if the US region can respond faster for another request, the Cortex will use that region instead. So in every moment, the Cortex assured that every request is matched with the best option available. Okay? Now I want to talk about the operator. Maybe some of you are wondering, why do we need the custom operator for that? The response is pretty simple. Kubernetes doesn't care about the pod and the PV collocation. So this characteristic is critical for a blockchain node if you want to maintain the lowest latency. So for that, we created a custom scheduling logic that allow us to run the pod, the PVC, and the PV on the same physical host. It's somehow faster to respond from the local node than making a request over the network. But the scaling was just the beginning, because we also need to address some aspects like backup and restore operation. I already told you that some blockchain can take a lot of time to sync, so we can't afford to start from zero, so we was forced to automate this process for backup and faster restore. Another important thing here was the scaling option. You can think of it like an extended horizontal pod autoscaler, but here we need to take into consideration the chain state. Also, we implemented disruption budget mechanism. In Kubernetes, you have the pod disruption budget that assure that a certain amount of pods can be taken down during maintenance. But here, we also need to take into account the chain state, and we want to control how we perform our upgrades. And finally, the last important feature of this operator is the custom metadata. This offers valuable information for our smart proxy layer. And with this information, our smart proxy layer can take important decisions about the routing, because we can somehow tell the proxy some important information like, hey, this is the implementation of the chain, this is the type of the chain, can be full or hive node, or if the node is healthy or not. Also, I want to be transparent with you. Creating this custom operator is also some tech debt that you choose to own. For example, if you update a third-party tool like Prometheus, we are using Prometheus for monitoring the resource consumption. If you upgrade the Prometheus, you also need to upgrade the operator itself to remain compatible with this tool. And because the operator is our control plane part for running blockchain nodes, if you commit any bug or misconfiguration, you can affect many blockchain nodes at once. So you need to treat this operation with high discipline. Okay, I will continue to talk about the storage management. This is one of the most important operations that we do in our cluster. For storage management, we are using OpenEBS. For those that are unfamiliar, OpenEBS, it's an open source project from the CNCF landscape that brings the storage management native in Kubernetes. That means instead of managing disk or nodes or volumes outside of Kubernetes, you can use OpenEBS, and you can treat all these concepts like Kubernetes object in the same declarative manner. Here, in OpenEBS, you have multiple data engines, and we choose to use multiple data engines because not all the blockchain have the same storage characteristic, and we want to use the right tool for the right job at the moment. The most important thing that we unlock here was the volume snapshot property that allow us to take a snapshot from a fully synced state, and you can start a new node from that snapshot instead of waiting for sync from scratch or to download from the latest snapshot from an S3 bucket or something like that. So also all these data engines have some trade-offs, because some of them doesn't support this volume snapshot capacity, and some of them have some limitation regarding the maximum size of the volume. I will let Marton to continue now.
Thank you, Mihai.
Thank you.
So let's talk about our deployment strategy. It is really simple, and we like simple because it's easy to follow. On the left, we have GitHub as our only source of truth, where everything lives, from auxiliaries, infra charts, the core chart, which I will be talking about soon, the operators code, node deployment, configurations, and everything. And then Argo takes it and builds a bunch of Argo applications, and it basically manages it on a app of apps pattern. And then it is deployed to our many clusters. We, as my colleagues said before, we have multiple regions. We also have multiple technologies. So we have redundancy and fallbacks. We have pros and cons on one of them, and other pros and cons on the others. And obviously staging clusters, because those are really important. Key part of the RPC platform is the core chart. In blockchain, all of the nodes and technologies are similar but different. And basically, they all rely on execution layers and consensus layers, but some of them integrate the DB inside of the execution layer. Some of them run a classical DB like Postgres. But we need to plug all of these into our infrastructure. So at first, because this was made for L2s and rollups, which were very similar, they used the same binaries. It was basically Arbitrum and Optimism. We implemented everything into charts and then had very minimal config files for deploying applications. But after a while, we realized how important RPC platform is to our mission, and we had to generalize it more. So now we basically use a big core chart that has a bunch of moving parts, and it just basically injects everything into our infrastructure. So we have bigger config files, but we have much more flexibility. When a customer comes to us and asks us to change the configuration to try something out, or maybe we have to upgrade, then it's much easier to move little pieces. So if we want to go deeper a little bit, we can look how a blockchain node actually looks like in Kubernetes. It basically has 3 layers. First, the init containers that bootstrap the whole environment for the blockchain, like initializing databases and downloading config files that are similar for all of the deployments. Then we have the blockchain containers, which can vary from 2 or up to 5. Some chain families use just 1 binary, some of them use 2, some of them use 5. So this is why we need to be very flexible. And then we have the third layer, a health checker that we developed, basically to check if the node is synced with the network, and it can be added to our smart proxy layer for serving requests to our customers. So our goal with Kubernetes was to scale fast. But if we have a custom proxy layer that has to be configured to serve traffic, and we, in the case of a traffic spike, we scale from 2 nodes to 10 nodes, how do we configure that layer? We're not going to do it manually, obviously, because until we merge the PR, the traffic might be gone, and there might be impact. So we have a external reconciliation loop that basically talks to the Kubernetes API. It gets the resources in the cluster, it derives a desired state, and then goes to our central configuration API and basically configures the smart proxy layer to do its job. So I want to be honest with you. Although RPC platform solved a lot of our problems, it cut our costs, it made us faster, there are still some challenges. Horizontal scaling is still pretty slow because we work on bare metal, and ordering a server takes time, and provisioning it and adding it to the cluster also takes some time. Another big issue is blast radius. So because we started beam packing and putting everything on Kubernetes, if a server goes down, we have multiple chains impacted, whilst before that, when we used bare metal, if a server went down, only that node was dead. So that's why we have a bunch of redundancy layers. Time to sync and expand, it's still slow. There are chains that take weeks to sync from Genesis, and there are chains that have 15 terabytes of data, and downloading a snapshot for that, it's still pretty slow. But thanks to some storage engine technologies, this can be made faster. Rollback operations are still pretty hard because this is an inherited problem from blockchain. Let's say you upgrade a node, it starts progressing, it hits a bad block, it cannot progress further, then you can't just, some nodes can roll back, but some cannot, and basically sometimes you have to delete data and just start over. So it takes a lot of time. And also, latencies can be an issue. First, we used DNS resolution based routing, but now we use IP-based routing internally. And we also have problems with workloads fighting for resources on the same machines, which can also be pretty painful. Thank you for your attention. I hope you have time for questions, but if not, please come up to us and we'd love to chat. Thank you.